and thank you for the introduction. So I will be talking about oceanic transports today and the calculation of those for reanalysis and ocean models with our new tools, StraitFlux. First of all, thanks to my colleagues, Leo Heimberger, Michael Meyer, and Isabella Winterer from the University of Vienna. So I guess we all know of the importance of oceanic transports for the global climate. They have an important role in distributing mass, energy, nutrients, and therefore an important role in the energy and mass budgets of the global oceans. Thank you. For example, ocean temperatures and currents are also listed as essential climate variables, at least as of now. We heard some will be cut, I hope not those, but we'll see. And so an accurate monitoring of those variables is really important. And we have multiple measuring lines in the global oceans. So for example, in the North Atlantic, as seen here, okay, the mouse is gone. Never mind, as seen here in the figure. So we have the rapid section, we have the Ocean Array further north, and even further north we have moorings in the Greenland-Scotland Ridge and the Arctic sections, which measure deep water velocities and other sea state variables like salinities and temperatures, for example. But still, observations are limited in space and time. Therefore, it's of course desirable to get transports as credible as possible from ocean reanalysis, which can be a bit challenging for us users at least, as the direct comparison to model-based transports can be a bit of a challenge due to the implied modeling grids. So of course it's natural that ocean models have to avoid singularities over the ocean, and therefore grids like, for example, tripolar grids or displaced dipolar grids or also unstructured grids are used. However, those pose some challenges when calculating the transports concerning the direction of the flows, concerning the signs of the velocity components. So for example, when looking at the displaced dipolar grid in the middle, at Frem Strait, if we move towards the artificial North Pole, which is over Greenland, instead of moving northwards, we actually move towards the southwest. So this introduces some challenges concerning the directions of the actual flows. Also concerning the boundary conditions used by the models and the Arakawa partitions. And so when calculating transports from a large ensemble of models, for example, from CMIP6 or also a large ensemble of reanalysis, the transport calculations can be quite time-consuming, and therefore we've introduced StraitFlux, new Python tools for the precise calculation of volume, heat, salinity, and ice transports. They work on various modeling grids and were tested for a handful of reanalysis and a large ensemble of CMIP6 models. Basically they work using two different methods. So the first method, I think this is the most common method, the so-called zigzag method, where if we have a strait, like in this example, the red line is Frem Strait, so between Greenland and Svalbard. We want to follow this strait as closely as possible along the grid cell faces, and then integrating along this unbroken line, we get the net transports flowing through the strait. But then for some assessments, we want to look at the vertical plane to really look at the currents flowing in and out of the system. And therefore, we've developed a second method, the so-called vector projection method, where we really at all surrounding grid cells, the currents are projected in the direction of the strait, and in the end we obtain quite nice cross-sections of the flows, which we can directly compare to observations, as seen here in the right figure. So here we have Frem Strait again. We see the biases of observations from the ArcGate project minus GLORIS 12. So we can assess quite nicely where are the currents in the reanalysis too strong, where are they too slow. And so using those methods, we've performed multiple case studies. In those case studies, we've actually focused on the European side of ocean reanalysis. So we've used the GREP ensemble, which consists of CGLORS from CMCC, FORM from the Met Office, OROS-5 from ECMWF, of course, and GLORIS 2 V4 from MacArthur Ocean. And additionally, we've also looked into GLORIS-12, the higher resolution product, and also a larger ensemble of CMIP6 models. So what's still missing is the American and Japanese side of ocean reanalysis, which would be nice to look into next. So the first case study is at the Greenland-Scotland ridge. So you can see where this is at the top right plot, if you don't know it. So it's between Greenland, Iceland, and then moving on to the east to Scandinavia. So we compare the reanalysis to available observations. Those observations, they are derived from moorings in a mass-consistent way in an inverse modeling approach from Takamasa Tsubuki. And are displayed as the red line in the figure. And so what do we see? So this is the total heat flux through the whole Greenland-Scotland ridge. And we see that in terms of variabilities, the reanalysis actually perform reasonably well. And especially for the single branches, so really for the Greenland-Iceland part, the Iceland-Faroe part, and so on. Also the mean values are represented quite well. However, if we look at those net transports, and if we look at the table to the right, we can see that the net heat inflow into the Nordic seas is actually underestimated by all reanalysis that we've used when compared to the observations. And so then next we use the cross sections from our cross section method and divided the flows concerning to the properties into Atlantic water, polar water, and overflow water. And then we found that those biases in heat transports are actually mainly caused by an underestimation of the Atlantic water inflows into the Nordic seas. And especially for the individual branches, we also found some indications that the higher resolution product performs a bit better in terms of variability and mean. And this study was part of the last, so the 7th Ocean State Report. Then another case study was performed at the Indonesian through flow region, as seen at the top left. So we've looked at 4 different straits. So we have here we have Makassar Strait, we have Lombok Strait, Ombay Strait, and the Timor Passage. And again, we compare reanalysis to available observations. So in the time series figure, we see the volume transport via Makassar Strait, where we have the longest observational record, which is shown here in red. And we see reasonable agreements between reanalysis and the observations, both in terms of variability and also mean values. So if we look at the bar plot at the right bottom, we see the biases between observations and reanalysis for the different products. And we see that actually the reanalysis, they show a flow that is too weak in Makassar and Timor Passage, and a flow that is too strong in Lombok and Ombay Passage. And then looking at the purple bars in the middle of the bar plots, this is GLORIS-12, and we see that at least at Makassar, Lombok, and Ombay passages, GLORIS-12, it actually shows an improvement over the quarter-degree reanalysis. So summing up in this study, we see that the complex structure of the ITF region is still challenging for the reanalysis, but we see that the high resolution products especially, they show a little bit of a more promising outlook. Then we've also performed some studies in the Arctic, assessing the energy and water budgets. So already back in 2019, Michael Meyer, he introduced new observation-based estimates of the coupled energy budget, also including ocean reanalysis. And in 2022, we've duplicated the study for the water budget, and we were able to also close the water budget using an variational optimization approach and including ocean reanalysis for the transport estimates. And then following this, in the study published this year, we've assessed the energy and water budgets also for climate models. So here we have to the left the net oceanic heat transport into the Arctic, so via all 4 Arctic straits. The black solid line shows the mean of the GREP reanalysis, and the black dashed dotted line shows the observations. So we see that the reanalysis are a little bit too low, but in general, they perform reasonably well. But when compared to the CMIP6 models, we see that the models are all over the place. So we have huge biases and large uncertainties. Yes, can also be seen in the bar plots. So the black bars to the right show the mean values of volume transports top and heat transports bottom. And the last black bar to the right is the grep is the mean of the grep reanalysis. And the blue bar is from observations. Okay, and what we are working on right now is OSNAP, again, comparing reanalysis to observations. And here we have OSNAP East, and for the time series to the left, so this is the heat transport, we see that the reanalysis actually don't really correlate with the observed OSNAP values, also seen in the table in the middle. And what we tried then, so we played around a bit, and what we tried is to set the sections where we actually don't have any direct observations to the climatologies also in the reanalysis. So all of the black sections in the top right plot were set to the climatologies in the reanalysis. And especially when doing so for the temperature, we find a significantly improved correlation. So shown here in the dotted lines, and looking at the table, we see that the correlations, they move up significantly to 0.4 to 0.7. So this suggests that maybe some variability in the observed OSNAP array actually comes from an undersampling of the real variability in the unobserved regions. Yeah, so summing up quickly, so we now have StraitFlux, which really allows for a fast and precise calculation of transport and cross sections and an easy comparison to available observations. It also has a function to quickly calculate the meridional overturning circulation. And yeah, we've used it already for multiple case studies and already showed some of the usefulness of the reanalysis, but also found moderate uncertainties and biases which still need further analysis. And yes, Romain talked about it today. So in the comparison projects like the upcoming MER-EP, they're really important to assess the strength and limitations of the reanalysis, for example, concerning oceanic transports. Yeah, so that's all from me. Thank you.